Okay, this is the second video on section 7.2. We're going to look at two quick topics. We're going to look at finding arc length and surface of revolution and parametric equations. So for the arc length, given the plane curve defined, so place curve, I should say plane, given the plane curve defined by the parametric equations, x equals x of t, y equals y of t, where t is between t1 and t2. Assume that x of t and y of t are differentiable functions of t. The arc length of this curve is given by s equals the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. And I believe your textbook has a derivation of the arc length formula. So let's go ahead and try it out. So an example here, we're going to find the arc length of the curve x equals a cosine of theta and y equals a sine of theta, where theta is between 0 and 2 pi. So we need to find dx d theta, which is negative a sine of theta, and we need to find dy d theta, which is equal to a cosine of theta. The arc length is going to be equal to the integral from 0 to 2 pi, negative a sine of theta squared plus a cosine of theta squared, and then square root of the whole thing, d theta. Okay, so it's going to be equal to the integral from 0 to 2 pi of a squared times sine squared of theta plus cosine squared of theta, d theta, and that whole thing under the radicals, the square root of a squared times the quantity sine squared of theta plus cosine squared of theta. It's going to be equal to the integral of 0 to 2 pi of the square root of a squared times 1, because that's what sine squared plus cosine squared is equal to, so just square root of a squared d theta. And we're assuming that a is positive, so square root of a squared is a. We can slide that out of the integral, so we have a integral from 0 to 2 pi d theta, and that's a 1 d theta, so the integral of 1 with respect to theta would be theta. So this becomes a theta evaluated from 0 to 2 pi, which is going to be equal to 2 pi a. Now this is just a circle of radius a centered at the origin, and the arc length here is going to be the circumference, which is 2 pi r. In this case, it's going to be 2 pi a. Okay. All right, let's look at surface of revolution. So surface area generated by a parametric curve. Given a smooth parametrically defined curve C, x is equal to x of t, y is equal to y of t, where t is between a and b, that does not cross itself on this interval. The surface area formed revolving C around the x-axis is given by s equals 2 pi, integral from a to b, y of t, square root of x prime of t squared plus y prime of t squared, that's the end of the square root, dt, provided that y of t is greater than or equal to 0 on this interval ab. Again, I think the derivation of this is in your textbook. It's similar for the surface of revolution formula in rectangular form. So let's do one example here. Let's find the surface area of the curve x equals 15 cosine cubed theta, y equals 15 sine cubed theta, where theta is between 0 and pi over 2. So we need to find the y of t, which we already have, which is 15 sine cubed of theta. So this should be a theta here, not a t. Okay. X prime of theta, sorry about that, is equal to negative 45 cosine squared theta and sine of theta by the chain rule, and then y prime of theta is equal to 45 sine squared theta and the cosine theta by the chain rule. So our surface of revolution is going to be equal to 2 pi, integral from 0 to pi over 2, 15 sine cubed theta, and then we have the square roots of 45 minus 45, cosine squared sine theta, and that's all squared, plus 45 sine squared cosine, and that's squared, and then d theta at the very end. So it's going to be 30 pi, so slide out the 15, integral from 0 to pi over 2, sine cubed theta, and then we're going to have a 45 squared, so we're going to slide that out of the, not out of the entire thing, we're going to factor it out, so 45 squared. And then we're going to have a cosine sine squared, and then a sine squared cosine squared. So that's going to give us a cosine squared theta and a sine squared theta in common, so we're going to factor that out. When we factor that out, we have cosine squared theta plus sine squared theta left over, and we're going to integrate that with respect to theta. So we're going to have to finish this up on the next slide here. So let's go ahead and rewrite that whole big long thing there. Okay. All right, so we have 30 pi integral from 0 to pi over 2 of sine cubed theta times 45 cosine theta sine theta d theta. So in that radical, the cosine squared plus sine squared became 1, so then we had the square root of 45 squared times cosine squared times sine squared. So square root of 45 squared would be 45, and then we're going from 0 to pi over 2, so both cosine and the sine are positive, so the square root of cosine squared and sine squared in the interval 0 to pi over 2 are going to both be positive cosine and positive sine. Okay, so this is going to be 45 times 30 is going to be through 1350 pi. And then we got the integral from 0 to pi over 2, sine to the 4th theta, cosine theta, d theta. So this is a simple u substitution. U is equal to the sine of theta. Du is equal to cosine theta d theta. Let's go ahead and convert our limits. So when theta is equal to pi over 2, u is equal to sine of pi over 2, which is 1. When u is equal to 0, when theta is equal to 0, u is equal to the sine of 0, which is 0. So now we have 1350 pi, integral from 0 to 1, u to the 4th du, which is going to be 1350 pi, u to the 5th over 5, evaluated from 0 to 1. And so that surface of revolution is going to be 675, and in this case it would be units squared. Okay, so that is it for 7.2. So we got two more sections to look at, 7.3 and 7.4. So we'll see you next time.